I'm talking about Go and SQLite. I'm going to talk about it in a few different ways. First off, I worked at Google for 8 years. I was on the Go team. I did a few other things there. And I left a few months ago. And now I'm doing my own thing, I guess, which just means programming on my own time. Anyway, along the way at Google, I learned a lot of things. Some of them good. Actually, a lot of them good. I learned a ton about programming and a ton about teams and how they work. And I want to bring those things with me into my new work. Make sure that things I learned about code review, about testing, about how to deploy systems, about how to monitor systems and make sure they're working, how to canary out new builds and see how things work. All of these are great techniques, and I want to use them all. But there's a problem, which is that when you're at a big tech company and you have a bunch of engineering problems, and you make a list of the engineering problems you have to solve to launch a product, you go and solve them, and if you can't solve them, you just go and find more engineers and you get them to solve them. And if you want to be cynical about this, you can use the Futurama meme about killbots. You just throw wave after wave of engineer at the problem until it's solved. But that's cynical, and the truth is, if you have a lot of money and you have a big problem to solve, you use the money to solve the problem. It's completely reasonable. But it doesn't work for me because I don't have all the money. So I have to just solve it myself, and so now I'm between a rock and a hard place. Like, I need to build a product, but I only have these tools, so what do I do? So I've been going through, from the ground up, every single thing I've ever used and deciding what I can keep and what I have to throw out. Just because I don't have time. And what I've come up with is Go and SQLite as sort of the two big key components that I'm keeping, or reintroducing in the case of SQLite, because they don't get used much at big tech companies, at least not in the cloud. So this is all, of course, a part-time project. This is what I spend most of my time doing. It's taking care of this guy. I thought I just needed an image in my talk, and he's cute. So SQLite, or SQLite, or SQLite. You can call it whatever you want. I'm going to try and rotate through all the different ways of pronouncing it through this talk, keep everyone on their toes, entertaining. It's a database. It's a relational database management system, as they used to call them in the 80s. And its distinguishing feature, it's not unique anymore, but its distinguishing feature is it's a self-contained C library that keeps the entire database in a file, on a disk, in a file system. Really old school ideas. And it's great. It's so wonderful. Everything about it's terrific. And if you've ever used DBase 3, it's just like DBase 3, except good. If you've never used DBase 3 and never heard of it, great. And as I said, files, SQLite, starts with this as a big assumption. There's a Unix file system, or something Unix-ish, Windows file system, something where you can put a file and you can edit it, and maybe you can even lock it and tell other people it's locked, maybe sometimes. It's a good assumption, and it's one we throw out a lot, and I would like us to throw it out less. And that's one of the things I will be talking about near the end of this talk. But instead of talking, let's do a demo, because demos are fun. Or at least let's see if I can do a demo. I don't think I've ever done a live coding demo, and I'm going to do some data science, I think they call it. I don't know, find out. I have a file I stole off Kaggle. Kaggle's really good, by the way. And if you take a look at it, it's Shakespeare. It's Shakespeare line by line, all of it. There's not actually a lot of it. It's about 10 megabytes of data. Would have been a big deal once. So we're going to put it in SQLite. We're going to do a couple things to it just to see how it works. So let's give it a go. So we're going to create an SQLite database. Done. All right. Now let's use some special tools. This is the SQLite command line utility. It comes from Richard Hipp, who made SQLite on the SQLite.org website. And it's got a couple of non-SQL. Oh, let me back up. Who here has used SQL? Great, all right, that's everybody. Who here has used SQLite? That's everybody. So I can just skip all of this. Yeah. No, it's wonderful. It's been around nearly 20 years now, and it's just one of those ubiquitous components of programming for me. It's right here on my Mac. I didn't install this. This is the binary Apple shipped me. It's wonderful. It's on everyone's Android phone. It's on everyone's iPhone. It's in space. If you can think of a place, they put it there. It's in Airbus control software in the flight control software. I'll get to that in a second. So anyway, I don't think this bit is, and hopefully the Shakespeare isn't. Shakespeare's good, by the way. He's in that very awkward place of being both excellent and overrated at the same time. You can blame the Victorians for that. Back in the 19th century, we can blame them for just about everything. But he's still really excellent, so you should read him. Or you should put him in your SQLite database. So we've knocked our SQLite command line utility into CSV mode, and we're going to import that CSV file. It's got some nice little tab completion, which is good because typing in front of a crowd is really something. We're going to put it in a table called import. Okay, we've done that. If we take a look, it created a table named import, and it picked the first line of the CSV and used that for the column names. And we could take a quick look at that, like this. Just look at the first 10 rows. Yeah, that looks about right. That's basically what we saw when we took a look at the top of the file. We can like count that and make sure it makes sense. Yeah, it's about 100,000 lines in there. Okay, so now let's manipulate that data a little bit and then do something with it. So let's move it all into a new table called plays. And we'll have a row ID on that table, integer primary key. And here's something interesting about SQLite. That is me giving a type to a column name, row ID, and specifying it's the primary key of the table. But all these other columns, I'm not even going to bother doing that because SQL's type system is terrible, and SQLite did the sensible thing, which is to ignore it, which is wonderful. So now we've got a new table here, and if we just look at the schema again, you see we've got this new table I created. So now let's copy all the data from one end to the other, and we'll go insert into plays, and use the insert select syntax, which is great fun. So this is just the output of the select goes into the other table. So we're going to take the row. We're going to select. Oh, it's not called row anymore. Ooh, look at this. My notes are out of date. We're going to select data line as row ID, and I wonder if we have to convert it to an integer. We'll just see what happens. What could go wrong? Then we'll take play. We'll take player line number, and we'll rename that as our line number. And, okay, we have this act scene line thing, which if you looked earlier, if you were paying attention, I hope you weren't because it's too much data. It's a number dot. It's sort of like a sembar value, only it's act scene line. Let's split those out into columns, and let's do like a semi-competent job of that. I believe there's a bug in this, which I will let you, the reader, find and fix. So what I'm doing here is I'm treating act scene line as a string, and I'm slicing into it and taking out the first character as the field act. I'm going to take out the third character, which is after the dot, as the scene, and then I'll take the rest as, or after the second dot, and we'll just take the next 5, say, as the line number. That will do. I missed a what? I missed an as. I did miss an as, thank you. That is the kind of heckling I can really appreciate. Player line as text, and then we have to say where we're coming from, import. Let's see if it worked. Oh, it didn't fail. From, and then plays, limit 10. That looks about right. And look, we have a whole bunch of numeric fields now where we had the string field earlier. Wonderful. So now we can do some, let's look around our Shakespeare. There's a famous soliloquy that we all know from school by a guy who liked to procrastinate. Procrastination never ends well, is the lesson. Or at least it should be. He rattles on a roof for a little while about what to do. I'm pretty sure he said that, but I can't find it. So this is probably like a capitalization issue, or there's going to be some punctuation in here or something. So let's improve our search of that a little bit, because what I really want is to search like I'm using Google or something, and what I'm actually using here is a string matching thing, so that's no good. So let's just do some full text search engine stuff, because that's always great fun. So we'll create a virtual table, play search, using FTS5. How's this? Plays row ID and text. Here's a new table, and now we're going to insert into that from our plays table, and we'll just copy in the row ID and the actual text that we want to search over rather than everything from the plays table. You could just use this as your main table and skip that, but I will keep them separate, and I'll explain why I do that in a little bit. Can I move the mic? Is that better? And speak up? Oh yeah, I have a mumbling problem. Thank you. It's insert into play search, select. We're doing an insert select. Let's try that. Okay, so now we've built a full text search index that we can take a look around in. So where earlier we went for select star from plays, let's instead go for select star from play search, where text, and instead of like we'll use the match keyword. There it is. Okay, so there was a capital W, and tis, of course, has an apostrophe at the beginning of it. That makes sense. And it's on row ID 34,231, which, as everyone who remembers their Shakespeare knows. So we're done. We've got a full text search engine. All of this is just in the default. I didn't rebuild this or anything. Everything just, you have a full text search system just sitting on your machine that you can use trivially like this. And just to show off some SQL, let me see if I can type this out. So let's try and do a join and get all of we're accessing a field of the table, and the field names are overloaded, so I'm using a qualifier. So we're going to do the previous query we did in place search, and we're going to do an inner join, which is the only join I can ever remember, and it's the join where you go one-to-one with another table. So we're going to inner join the plays table, and we're going to do it on play search plays row ID equals the plays row ID, which is where it came from, if you remember my select insert from earlier. And then we're going to put our where clause back on this, where text match, where that is nowhere in the mind. Ambiguous column name text. So this one here I didn't qualify. Both tables have a text. Which one do you mean? I mean the one in the full text search index. Okay, there we go. So Act 3, Scene 1, line 65. Hamlet says that. Yes, he did. Great. So that's SQLite. That's everything you need to know. Wonderful. If we remove that first import table I created, and we clean up after ourselves, and then we exit, you'll see our database is about twice the size of our comma separated value file. You remember our database has 2 copies of all the text in it, because there's a full text search index and the original plays index. So it's a really efficient file format too. It's actually pretty good. So that's SQLite. That's really everything you need to know. That wasn't the worst thing that could have ever happened, that demo, so let's declare victory. Let me check my time. A little bit over, but that's all right. I'll cut stuff. So, SQLite, you can use it from Go. There's a Seeger driver. There's actually several Seeger drivers. If you look around, if you go to go.org, it's very confusing. This one's pretty good. This has been around for a very long time and does what you need. You can use the database SQL package. You can use SQLite. And it looks kind of like this. And this is that join I just did. Yes, I prepared some notes for my live demo. Written in Go, and this does all the work. It opens up the database, it does the join. It uses query row, which uses reflect under the hood, to grab all of the fields out into values and then prints them back out for you. And so if you run this, you'll see basically what you saw when I ran that last select query by hand. And that's all you really need to get started to be using this stuff. But there's all sorts of other fun things SQLite does, which I'm going to talk about during this talk. And that Seeger wrapper and none of the others support them. So I wrote one. It's not a database SQL driver. It probably should be at this point, and so I'll get around to writing that one day. But it's actually just as close a wrapper as possible to the SQLite API in Go. And the key things it uses that I'll mention here are streaming blobs, session extension, and shared cache. It has a few other neat tricks, but that's the big one. So this is a great time to have an aside about Seeger, which I was told to have. Seeger and I are great old friends. I've used it for many years for many things. Everyone hates it. It's for reasons, for pretty good reasons, really. The usual reasons people hate it is, oh, I just brought some C code into my Go code, and my C code is terrible. And that's true. Most C code is terrible, and you're much better off if you rewrite your C code in Go. It's a good general rule. That rule doesn't apply here. And the basic reason it doesn't apply is that when we use programming languages to build programs, programming languages have all these features, and the features help us be more productive, they help us work better in teams, and they help us write correct code without bugs. You're not writing SQLite, you're just using it. You don't have to worry about the SQLite team and how they're building their C code. You don't have to worry about their productivity either. Somehow they've built an entire database into a C file and given it away. And when it comes to bugs, all of the tools we use in databases, in programming language, to avoid bugs are shortcut ways of testing. So types, all these things that we use are just us getting around the fact that we need to run the program and try it and see if it works in our actual environment. SQLite has all the testing. They tested everything. It's done. It's completely correct. It's not. It's got bugs. But it's the most tested program that you can download on the internet, I claim. I think there are a few things that have better testing than SQLite, but they mostly live in avionics somewhere. and they're much smaller than SQLite. And there's a wonderful document about this on the SQLite website you should take a look at. It's astonishing. It's the most correct part of your program. You are not compromising your Go program by introducing SQLite into it. Cross-compilation is harder, that's true. It's harder. You have to have a C compiler for your target environment on your local machine, which means you have to install a Linux compiler on your Mac. It's the practice of this. That's annoying. There are packages to help. I can't really avoid that. Your initial Go build is slow. It used to be every Go build was slow, and you had to remember to -i and all this stuff, and no one knew about that. But that actually got fixed on the last Go release. Your intermediate SQLite package doesn't get rebuilt each time. So you only notice that the first time. It takes 30 seconds to build on my dinky little MacBook. And after that, it's 1 second to get your binary. That driver I showed you earlier, unfortunately, wraps some SQLite features which are hidden behind C macros at build time using Go build tags, which is not great. I really don't recommend doing that. You have to get in and modify the driver yourself. It's not fun. I have a branch on my little low-level driver where I'm working on this. I'm waiting on the next Go release, which has a feature I need. There should be some fun stuff there. So where do I use this? I use it in a bunch of places, and that's actually a very important point I'll get to. So let me start with the client. I write iOS apps, macOS programs, and a thing for Windows. I have them in various states of readiness. And I do a lot with this. I have entire copies of all user data on the local device. So I have to do a lot of heavy lifting locally. So this is where that full text search I showed you earlier comes in. SQLite's really quite good at this. It does mean I have to think a lot about cloud syncing, or you could call it backups to the cloud, because all of your data is local, and how to deal with multiple clients interacting, which SQLite also helps with, which I'll show you in a moment. But just a audience question. How many people use Go on the client? Yeah, that's not very many. Okay, that's very few hands. Who has done client development work? And keep your hand up if you used SQLite on the client. Okay, so far more people have done client development work than have used Go on the client, which makes sense. And it looks like more people have used SQLite on the client than Go. So I claim there's nothing controversial about using SQLite on an iPhone or on an Android app. There is something kind of controversial about using Go for this. It's not very widely done. And again, if you're trying to cut features, you have to worry about, are you doing something really unusual that's going to lend you in a bunch of bugs? So the big question is here, should I be using Go for this at all? I claim I should. I should because I use Go for my servers. And I have only so much space in my head. And that's a big part of the problem of being one person, is I can't just go and learn other things. Or I can, but then something else falls out of my head. And all of this consumes hours. And so I need to cut down the space of tools I use. And so I use Go on the client. And it works pretty well, actually. So back to the cloud sync problem, back to SQLite. There's an extension to SQLite called the session extension. And when you create a database connection, this is the Go API from my low-level driver, but there's a C API that looks roughly like this. When you create a database connection, you can create a session on it, and then the session object sticks around. Then you can use that connection to select, insert, update, delete, all the usual things you do, run transactions. At any point, you can call the change set method on the session and get back a blob which contains the difference between when you created that session and where you are now on that database. So you can take this blob and you can store it somewhere. You can grab an old copy of the database from some other time and then read the blob back and apply it with the change set apply method. So you can take version 1 of SQLite database, make some changes, record a patch set on that, and then take another version 1 and bring it back to where you are now. So this is how I do client sync and backup. I have on the client device, I periodically record a change set, send it to a server. The server applies it to a copy of the database it's keeping around. And then I keep a stack of change set applies that can be sent down to update other clients. This is a little bit tricky because, as you can see in the change set apply parameters, there's a conflict function. So you have to be very careful about the way you design your database so that you don't create lots of conflicts. The biggest thing there is row IDs. So row IDs in SQLite, as everyone knows, auto increment as you create rows. That just means they conflict all the time, so you need to start randomizing those, or you need to start bringing them out of some range that's been reserved for each client. And then, of course, you need to make sure that you have lots of data that's append-only or delete, or things like that, which minimize your conflicts. It works really well. It's been great fun using that. Just to go back, the session objects are extremely small. They're very efficient. They're efficient in the sense that if you update a field in the database from 1 to 2, then 2 to 3 to 2 to 4, the change set you get out just has the final jump. It doesn't just record every statement and run them back. Another fun thing I found, and this is not as vital, but it is a lot of fun, is nested transactions. Databases have transactions. They're absolutely vital for doing useful things with databases. You begin a transaction is the SQL term, and then you commit one. There's another piece of SQL for creating transactions, which is the save point, which works exactly like begin, and then you release it to commit it. With the one difference that you give it a name, and then you can start other transactions inside it. And then you can roll back those transactions if you want. So here we have a series of nested transactions, and we roll back the inner one, so it doesn't apply. This fits surprisingly well into a little idiom I have in my Go programs that doesn't fit with the database SQL driver. And so it's kind of a sort of fun little invention. And that is at the top of every function I have that's doing transactional work on the database, I start a save point. So on the connection, I register, I give the save point a name, and then I defer a function which checks the error value I'm about to return from my Go code. So this function f returns an error, and the defer checks error, and if error is nil, then it commits the transaction. If it's not, it rolls back the transaction that this little f function was doing. And then at any point during this function, for reasons of database access through other functions or through you're parsing some data and it's incorrect, you can just return and the whole thing rolls back, which is a very lightweight way of thinking about transactions. Most importantly, you see here we call G. G can do all of this again. So it at the very top can register a save point and then can defer either releasing or rolling it back. And then you can call G completely out of context. You don't need to have to call it through F. It has its own self-contained transaction. As long as it logically makes sense as a transaction, you can do that. And I find that a surprising number of my Go functions actually do make logical sense as a database transaction. And so I do this a lot. The one thing is there's actually quite a lot of bookkeeping to get right inside that defer function because the SQL actions can fail and then you have to create errors for them and return those errors appropriately. And it ends up being like 50 lines of the defer block. So I have a little utility function that does this, whose syntax looks a little unusual the first time you see it, but you get used to it pretty quickly. And so at the very top of each of these transactional functions, I call save on the connection, which returns a function that takes a pointer to an error, and you pass in a pointer to your error, and then you defer that. And so you get this sort of gnarly one-liner, which does all of the work of creating a save point transaction and either releasing or rolling it back based on the error condition of the function you're in. And then you can do this in F, and then you can do this in G, and you get your nice nested transactions. It does a few other neat things for you. It picks a name of the save point based on the function you're in, and using a walking the call stack, which is surprisingly fast. And so you get quite nice error messages from SQLite when you've screwed up your SQL, telling you exactly where it went wrong. So those are tricks I use on the client. I use that trick on cloud programming too. So now I want to talk a little bit, and this is a little bit controversial, so I'll keep it short and vague and tell you it probably doesn't apply to you working at a well-capitalized tech company. I write a server in a process. So I build a process, and it's got like an HTTP port, an SMTP port, and a bunch of other things that it registers. And then I run it on a VM in an availability zone on a cloud hosting provider, one of the big three. And that's it. That's all I do. I over-provision the machine, because why not? It costs me like $50 a month, which makes it really easy for me to canary out a new one, divert some of the traffic. I have a little thing for doing that, little 1,000-line harness that I built, and that's it. And everything lives in this one process, and it kind of works. And this one process includes the database. It's got SQLite, and it reads a file on the machine. The file is stored on the NAS system. So I'm using Amazon right now. I've been trying the other ones, and they call their NAS system EBS. I'm going to go into that a little bit. But the key thing here is this is sort of like one computer programming. So I can scale my service until I hit the limits of one computer. And then it's all over, game over. I can't do anything more, right? Oh no, right? I can't scale. That's one of the things I have to throw away, right? Like, I can only do so much as one person. I can't build big distributed things that scale. It's just, I can't do it. Fortunately, I don't need to. It turns out one computer can do an awful lot. Like a lot. I mean, these scaling limits are you get 128 CPU threads, you get 4 terabytes of RAM, You can saturate a 25 gigabit Ethernet link. Like that's what I can build. And nothing I've built is coming anywhere near that. Nowhere near it. Like I can hit thousands of QPS in a moderately complex service on a very small VM, nothing like this. This is many tens of thousands of QPS. With hours of yearly downtime. There's some kind of SLA on an availability zone that's much less than multi-availability zone and geo-redundant services. But I claim that you can build most moderately large services doing this. In fact, a lot of the moderately large services I worked on at Google could have been built this way. And it's really unfortunate that Google never had a way to let you build moderately large services like this, because you could start a small team and get a service built and launch a product, and it would be pretty good doing this. And then you could rewrite it if it turned out successful, or throw it away if it's not. And it would have saved a lot of money. They don't care about money. That's great. But there are other advantages besides money. The other advantages are one programmer can keep the whole thing in their mind. A small team can. They can move really quickly. It's really easy to bring one of these up, bring it down. It doesn't involve a lot of the machinery that working with distributed systems does. I know that's extremely ridiculous. Like, who wants to write on a computer? But it's kind of fun. And it's really simple, and that's really important because there's only so many things I can keep in my mind. So a few technical details about this. SQLite has a write-ahead logging mode, which I highly recommend. Most people, I guess, don't know it exists, but you can just knock SQLite into write-ahead logging. It creates 2 extra files when you do this. There's like a little WAL file after your DB. And what this is instead of a rollback journal. So with a rollback journal, SQLite modifies your database inline and then writes a rollback instruction to the rollback journal, which says how to undo that if something goes terribly wrong, and actually does it in the other order. So if something breaks halfway, it can roll back the transaction. With write-ahead logging, all that happens is a transaction is written as sort of a change set onto a WAL file, and then periodically the system flushes the change sets into the database file. This means that you can be writing while other people are reading. So this is very important. SQLite's huge, big restriction, which makes cloud programming difficult, is it has one writer at a time. But it can have N readers, and now it can have N readers simultaneously with the writer, which means you don't get lots of service lockup. Writing with a single writer requires a lot of care. You have to be really careful not to block in the middle of your live transactions. A lot of those transactions I was using earlier are read transactions, which don't have these problems because they defer locking the database until you actually modify it. But no, it's the trickiest part. Don't access the network and block on something else while you're holding the write lock on the database, or else nothing goes well. So storage in the cloud. I mentioned I use Amazon's NAS system. They warn you it loses data. The numbers they give you don't make any sense. There's no way it loses that much data. I presume they're just trying to be really careful about it. They have a great snapshot to blob source system where it snapshots the change in their NAS thing to their big geo-redundant blob storage system really quickly, and you can program this, and I do. So I manually flush the WAL log of SQLite, the main one that sits on its own EBS volume. I have a package called really fsync, which triggers the S3 backup. So you just have to think about this in layers, right? Like the fsync on your nice EBS-based volume is better than your standard computer at home because it's a nice RAID array across the network, but not as good as it could be. So you have really fsync as your super backup system, and then you have a real backup system which gets it out of S3. Keep an open mind, of course, about this stuff. As they have the best NAS SLA, their numbers for disks are way better than the EBS numbers from Amazon. Google don't even seem to be trying. I couldn't find any of their SLAs. That's fine. They don't believe in this. It's not their game. But let me say, be wary of SLAs. Just don't believe any of this stuff, because I started reading their terms and conditions, and oh yeah, we lost all the data for your business that you've been running for 10 years, and it's all gone. Sorry about that. All the backups are ruined. We're going to give you 50% off your bill this month. Yeah, it's great. There's no symmetry in these SLAs. It's not insured. They tell you these big numbers and they give you a small discount if it goes wrong. So be super wary of that. Also be super wary of these geo-redundant systems. They claim they deal with long tail events to 50 billion nines or something. There's no way they can do that because it's written in programming. It's a computer. There are bugs in their software. It's not as well tested as SQLite. I know that for a fact. And what's going to happen one day is it's just going to lose everything because of some software bug. And it's oh, sorry. And again, their SLA doesn't require them to pay for it. It'll be really embarrassing. So anyway, don't trust any of this stuff. As part of not trusting any of that stuff, trust the availability zones, because we kind of know how those work. They're more reliable than everyone says. You can write a good system on that. I think I am out of time, so I'm going to skip a few things, but I am going to say, here's a slide about the disadvantages of this sort of one-process programming I do, which is there are some things you just can't do this way. You can't build a web search engine this way. You need more than 4 terabytes of RAM to store a public index of the internet. You need a lot more, so don't try and do that. There's all sorts of other fun things you can't do. If you find one of these problems, it's terrific. Build a distributed system. They're great fun. But work really hard not to. Try and do this first. You can't pretend you have the ultra-high reliability of these redundant systems. Pretending is really nice. You know, it's great to pretend we have 59s or whatever it is. There are real problems. Latency to global customers. You have to put this computer somewhere, and the speed of light is slow. CDNs are pretty good. You should use them. You can also consider geo-sharding, which is kind of neat. If your customer data is not deeply connected with other customers' data, if it can shard well, you can just move customer data closer to them. Just run a few machines and pick one near them for running it. It also makes cloud conferences kind of boring because they launch all these great products and you don't need any of them. It's really unfortunate. But there are advantages, and the most important one is ops. Like, again, my server looks exactly like my client software. If I get woken up in the middle of the night by some kind of page thing, I don't have to remember how PostgreSQL works, which, you know, I read a tutorial on to get it going, but I've forgotten now. It's exactly like the thing I use all day, every day on my laptop for my programming. And that's really important. You know, it just, you know, similarly, one process makes monitoring easier. You don't have the database fall over and the front end stay up or any of that stuff. It's all one thing, front end, back end database. You can do everything with pprof. You just look at your pprof output. You know whether your service is fast or not. You don't need to think about how the things interact or anything. You've removed a lot of protocols from everything. It's also really easy to bring it up on other hosts. It's easy to copy to Google or Azure or anything. So yeah, just don't use N computers when one will do, is what I have to say.